Okay, let's discuss second bullet point. So did you guys notice that it is an open interval on 0 and 6? If it were closed, this would be potentially a very different kind of question. So it is an open interval, so we do not consider endpoints. And so in all likelihood, we're looking for a relative extrema that might also double as a absolute minimum, maybe, but definitely we're looking for a relative minimum here. So if I am looking for a relative minimum, what are my candidates for relative extrema? Critical points. So critical points of the amount of sand on the beach. So I need to find essentially amount prime, or the rate of change of the amount. What would you guys say is the rate of change of the amount of sand? It's S of t minus R of t, and those are already rates, right? It's clearly explained up above, including the units. So I think we could say the net rate is S of t minus R of t. And we said earlier we were looking for critical points, and critical points are where that net rate is equal to what? 0. And I think you can tell, I think you can tell that for our realistic domain, the S of t minus R of t will always exist. There would be one point outside of our domain, negative 1/3. Yep, so our domain starts at 0 and moves forward instead of backward. And so that t equals negative 1/3 is not going to turn out a critical number that concerns us, at least. Let's see here. So how did you guys solve an equation like that? S of t minus R of t? Use the calculator, yeah. So use the calculator. Did you get one critical point when you did that? Okay, so one critical point was when t is equal to what? 5.10. 1011?
No,
11 what? 118, okay. Keep in mind, this is for everybody, but especially for like Jaden and Jeff. Remember, if you have a decimal answer, you got to go to 3 decimal place values at least. You can go more if you want. I got a question for you. Is this that I'm highlighting, is this very important to write down? Yes or no?
Yeah.
Very, yes. Because if you just write that, if you just use the calculator, if you set it up in your head, use the calculator, you just come up with that value, you really could honestly ask, where did that come from? But if what you did was write down S of t minus R of t equals 0, and then you write it down, well, that's clearly a solution to the equation. I know the calculator is active. And so because of the importance of writing down that equation, very often a point on some FRQ or free response question will be assigned to writing something like that down. So please don't neglect that. All right, so then what's nice about this is you do have that graph right in front of you, so it is quite easy to see the sign change pattern within S of t minus R of t. So when t equals 5.118, what kind of a sign change transition are we seeing within S of t minus R of t? Negative to positive. Good, that's what we were hoping for. So you could say something along the lines of S of t minus R of t changes from positive or from negative to positive. At t equals 5.118, therefore the amount of sand is minimized at that time. Okay, so that's what I would expect you to be able to do right now using mins and maxes. And is that the first derivative test, or is that the second derivative test we just used? First derivative test. You're right. You could have done math 8 with S of t minus R of t at 5.118 and used the second derivative test, I suppose. I don't know if that would have been, that probably would have been a little bit longer, a little more difficult since you had the graph right in front of you. So then veterans. Please notice it does ask that other question. It says at what time t is the amount at a minimum, and we just answered that, and we just justified that. It also asks, what is the minimum value? So this is very different. It's wanting to know what is the amount of sand at that minimum, when it's at a minimum. And so any ideas on what you'd set up?
Integral.
You're going to have to use an integral. What kind, a definite or an indefinite? I think a definite. You want the 2 limits there, right? So anybody have a thought on what that might look like as far as just a setup goes? Okay, integral from 0 to 5.118. of what?
S of t minus r of t.
S of t minus r of t dt.
Plus 25.
Did anybody forget the plus 2,500? Why does that plus 2,500 have to be there? Say again?
Because otherwise, I mean, like, that's just...
Does it end up being negative?
Yeah.
Okay, yeah, so the net change is negative,
Yeah.
which makes sense because we're at a minimum, right? Yeah. That 2,500 is how much was there to begin with. If the 2,500 wasn't there, you're kind of implying that it was 0 to begin with, but it was actually 2,500. So yeah, that would be the setup to help you find what the minimum amount of sand actually is. And I would definitely use the calculator at that point. Without rounding the 5.118, I'd use the whole thing. And add the 2,500 on there. Not something I'd expect you to be doing right now, especially if you're a rookie. If you remember that, it's awesome. We'll get into that when we get into our next unit. Okay, and then lastly, at what time would y of t, we're calling that the total number of cubic yards of sand on the beach, at time t, when would that be maximized? And I want you to use a graph to help you justify yourself. So use the graph in front of you. You probably already have that from the second bullet point. And let's see at what time you think that maximum would be. Maybe already. And that graph, at least on the interval 0 to 6, doesn't it look kind of like that? Is that pretty reasonable? Okay. So this is a graph of S of t minus R of t, which is the rate of change of the amount of sand. And so what we're going to learn when we get into the next chapter is that whenever a rate is negative, we've already talked about this, we're going to connect it with integrals next unit. Whenever a rate is negative, that represents something is decreasing, right? And so couldn't you look at this segment through all this and say, well, that all represents negative rate, therefore the amount is decreasing, right? So that, and this point we already found is 5.118. So from 0 to 5.118, the amount of sand is decreasing the entire time because the rate is negative. And then when you get over here to that 5.118 and this graph of S of t minus R of t transitions to be above the x-axis, or I guess above the t-axis, that would indicate that the rate is positive, which would indicate the amount is increasing, right? So the question then becomes, like, how do you quantify how much increase we got and how much decrease we got? Because that's going to tell us where the max is, right? So what could you use here to kind of help you quantify that and be like, well, I think the decrease was more than the increase, or the increase was more than the decrease? What are we looking at here? What do you think, Nick? So I'm not looking for an integral right here. I'm looking for a graphical.
The area in the decreasing part where it's negative
Mm-hmm.
is greater than
Yeah.
the upper area.
Looking at area. That's the key piece on the graph. And he just said the area below is bigger than the area above, right? And so since the area below is significantly bigger than the area above, would you say that way over here at 6, would you say that the amount at 6 would be more than the amount at 0 or less than the amount at 0? Less. Because we have lost a lot of sand and we gained a little bit back. And so that means out there at 6, the amount is going to be less than what we started with. And so at what time would y of t be maximized? I think we'd have to say when t equals 0. And what would be that amount? 2,500. Yeah. It didn't really ask for that, I suppose, but 2,500 cubic yards would be that amount. And it does say give a graphical reason for your answer, and Nick said it really well. Basically, the area below, which represents negative change, is bigger than the area above, which represents positive change. And so out there at 6, we'll have a smaller amount than what we started with. Does that make sense? Yeah. Okay. Hopefully an interesting way to look at it. Next unit, we will do this with integrals, and we'll get exact answers and all that stuff. Colin? What Nick said. The area below which represents a decrease in the amount of sand, is bigger than the area above, which indicates an increase in the amount of sand. Therefore, out there at 6, it's actually less than the amount we had at 0.
So that's enough.
Well, so this is a little bit of an intuitive approach, and there are actually examples and times where this approach of essentially saying, hey, that area is bigger than that area, therefore, ... But most of the time, especially in these cases where we actually have rules for the functions, we'll use an integral, and we'll be able to calculate, well, exactly how much is there at 6, and how much sand is there at 0. We can just compare and say, well, hey, that's a bigger number than that, therefore. So most of the time we'll do it analytically, but I thought we'd do it with a graph here. Again, since you guys haven't seen all the nitty-gritties of integrals and all that stuff yet. So, all right, let's go back to the person in the boat by the beach, which was number 1. I think we're going to settle an argument here today. Okay, so this is one of the tougher ones. I thought we could kind of do a little back and forth with this one and work together. I think this is very picturable, so I think it's maybe a good idea to draw a picture of this. It says a man is in a boat 2 miles from the nearest point on the coast. He is to go to point Q, located 3 miles down the coast and 1 mile inland. And then it gives some rates which he can row and walk. It asks us to determine at what point on the coast he should row so that he'll get to point Q. And a key phrase here is in the least time. So when you see that phrase right there, that kind of tells us everything we need to know about our general plan of attack. What are we trying to find? What are we trying to do? Minimize what? Time. So it's not necessarily minimizing distance. It's minimizing time. And those could be the same thing or they could be different things. Just depends. We'll talk about that. So I am going to just sketch out a real quick picture of this. So, the guy is in a boat or on the ocean or a lake or something. And here is the beach right here, whatever. So he is 2 miles from the nearest point on the coast. So this guy is right here. And this, is apparently 2 miles. That make sense? So here's the man out here in his boat. 2 miles from the coast. He is to go to point Q, which is 3 miles down the coast. So, and 1 mile inland. There's point Q. So this is 3, this is 1. That makes sense as far as the picture goes? So this guy has some options, right? If he was trying to minimize distance, if he was trying to do the minimum distance, what would he do? Well, yeah, diagonally, but specifically in which direction? He would go exactly straight at point Q, wouldn't he? If he's trying to minimize distance, he would basically just do that. But here's the problem with that. He's significantly slower in the boat than he is walking. He's a relatively fast walker at 4 miles per hour. Rowing a boat is hard. 2 miles an hour seems reasonable. So if he does that, he's going to be in the water for a long time, right? And so that's going to take maybe more time than he wants. He wants to minimize his time. There's clearly a hot dog stand or something at point Q he wants to get there. I don't know. So you could then say, well, that's not going to make any sense. Why doesn't he just do this, where he goes straight at the coast and minimizes his time in the water, and then he goes straight at point Q? That's another viable option as well, right? That's going to minimize his time in the water, but that's an awfully long walk. So, yeah. Or how about just time travel? Or
Option 3, he rents a plane.
wouldn't this be the worst possible option as far as time goes?
Yeah.
He's spending the longest time in the water and the shortest time on land. So maybe there's some point in between, right? Maybe there's somewhere in between that would actually be better. So maybe it's like, I don't know, something like this and then something like that. We'll see. Okay, do you guys have any questions so far? Okay, so let's do this. Let's just say that he's going to row towards that point right there, and then he'll get out of the boat and walk. We don't know exactly what segment of that 3 miles he needs to head towards. And so that's going to be our variable in this. I'm just going to call that distance right there x, representing, the distance from that nearest point on the shore. And so if that's x, what would this be right here? 3 minus x. That's right. Okay. So we get this nice picture labeled. Hopefully we've come to the conclusion that he's got to, head towards this point on the coast, x miles from the nearest point on the coast. But we do want to minimize time. We want to minimize time. And so maybe we should start thinking about, we need an equation that's going to tell us about time. So I've got a distance of 2 miles, a distance of 3 miles, a distance of 1 mile. I've got some rates like 2 miles per hour, and I've got 4 miles per hour. I'm interested in time. What relates all this stuff together? Okay. Those are the units for the rate, but aren't there other units like miles and hours? So what relationship relates? All the stuff we have up there. Say again? So that, I agree with you on the distances, and I think we probably will use that. But what I'm interested in is I'm trying to minimize his time.
Oh, okay.
And I'd like to start coming around to how do I get an equation that involves time and maybe some of that other stuff so I can put it all together, go back and use Pythagorean theorem and see how that plays into it. But I want to minimize time, so don't I have to have an equation for time? It's the old school one, right? It's seriously, algebra 1, right? Distance equals rate times time. Isn't that what you said? Distance, rate, and time?
Yeah.
Yeah, I did. That's one over.
Okay. So if you start with that and you say, all right, if distance is equal to rate times time, then wouldn't time equal distance divided by rate? So I'll write that down. T equals d over r. But then we have to admit that when he's in the water, we're going to have one set of information. And when he's on the beach, it's going to be a slightly different set of information, right? So maybe I should say time in the water, distance in the water, rate in the water. And maybe I should have another set of this information for on the beach. So TB equals DB over RB. Does that make sense? And then if what I really want here, if I want to minimize his overall time, how could I write just a single equation for his overall time?
TW plus TB.
Yeah, the two different times added together. And I think you have a good idea what you're doing there too, Jeff. That's good. But I want an equation. I don't want a floaty expression. So I'm going to say overall time equals time in the water plus time in the boat. Make sense? And then I can say overall time equals distance in the water over rate in the water plus distance in the boat divided by rate in the boat. Or beach, sorry. He's on the beach. Probably should use something. I should have used S for sand or L for land or something. Yep, good idea. Feel free to adapt as you want. The good news is don't we have RW and RB? So I can say then that overall time is equal to distance in the water divided by 2 plus distance on the beach divided by 4. Trying to really piece this out in small steps. Is this making sense? Okay, so really the final task before we can really dig into the calculus of this is we need to come up with a better expression for distance in water and distance on the beach. And this is where I think Jack's idea of the Pythagorean theorem would come into play, and I think Jeff is maybe a step ahead of me at this point. So wouldn't this right here be the distance in the water, that red hypotenuse, or that particular hypotenuse? And then this other hypotenuse, that would be the distance on the beach. So Pythagorean theorem here, it would be 2 squared plus x squared. So this would be square root of 4 plus x squared. So that would be for distance in the water. So t is equal to square root of 4 plus x squared over 2 plus the other one, a little more complicated. It would be square root of 1 squared plus 3 minus x quantity squared. all over 4. Pretty scary looking, huh? You could rewrite it a little bit. As simple as this looks, as simple as a change as this is, it's actually maybe a little bit helpful. Couldn't you rewrite this as t equals 1/2 4 plus x squared to the 1/2? Doesn't that automatically make it a little bit easier? Just the way it looks, at least. Plus 1/4 times 1 plus 3 minus x quantity squared to the 1/2. Something like that. All right. I got this wonderful equation for t in terms of x, and this is exactly what I wanted. So let's not lose sight of the fact that we're trying to minimize time. So what would be a candidate for minimizing time? Not quite where that equals 0. The derivative of that set equal to 0 / maybe dne. Agreed. So we got to differentiate this. We want to be super careful with that. So I'm going to write t prime equals 1/4 times 4 plus x squared to the negative 1/2 times 2x. I don't remember. It might be doable without one. Let's see here. Plus, I'm using a chain rule in there. 1/8 times 1 plus 3 minus x quantity squared to the negative 1/2. And then the derivative of that inside, let's see here, would be, 0. And then it would be negative 2 times 3 minus x, I think, if you use the chain rule right. It would just be 2 times 3 minus x at the first, but you got to multiply by negative 1 because of the chain rule. Does that make sense? And let's see here. What time did our class start? 35? So it ends at 25. So just for sake of time, let's just use the calculator here. You could clean this up a hair, but let's go ahead and use the calculator. We want to set this equal to 0. Remember, that's a pretty important feature here. Set that equal to 0. Use your calculator. Let's find that x value that will hopefully minimize this person's time in getting to the hot dog stand, or we'll say he's healthier, the chicken sandwich, the chicken salad stand. You could probably do this without a calculator. I'm just more interested in time. I want to do one Newton's method question, and I think
half an hour.
15 minutes. I don't think so. The key is you flip stuff down, and when you start flipping stuff down, you can get rid of it. You can multiply through, and it makes it a little bit easier. I don't know if that's the case here or not. I really don't. It's a good calculator exercise. See if you can get this input correctly.
Equals 0.
Anybody have an answer they think? Josh, what do you think it is?
Yeah, so I've got.
You do it. You see that I'm right.
Nice
I
going,
get schooled.
Well, I used different. I said that your 3 minus x was my x.
Well, so just tell me the other one then.
Okay, I would say 1 mile down the coast. So your x should be equal to 1.
Okay. So you got 2
Yeah.
because you said it. You flipped it around. Okay, that's fine. So Josh proposes 1. So based on that, I would say, yeah, we probably could do this without a calculator.
You got 1.9.
I want to get to Newton's method, so I'm
You got
just
1.91.
Probably answer.
1.91.
1.90.
Yes, sir.
On the derivative of the second time, the square root of 1 plus 3 minus x quantity squared over
Yep.
4. So you have 1/8 times 1 plus 3 minus.
So that's the derivative of the outside.
Yep, and that's squared
Yep.
to the negative 1/2.
Yep.
And then times negative 2 times 3 minus x.
So that's the derivative of the inside.
Yeah, and how did you get the negative 2?
So the 2 comes down in front. Well, the derivative of 1 is 0.
Yeah.
2 comes down in front based on a general power rule
Yep.
to the first.
Yep.
But then you have to multiply by the derivative of the inside. Because this is like a
yes,
double chain
yeah,
rule.
yeah.
And the derivative of 3 minus x would be -1.
Yeah.
So that 2 times -1, that's where I got my -2. So you got 1 also.
Just the number.
You just plugged it in wrong. So where you have some parentheses in the wrong place or something?
I was looking at the wrong thing.
Okay.
Looking X for 4, it's 1/2, -1/2.
Gotcha.
What a.
So guys, I think we got about 4 or 5 folks that are saying yes, we think it's x equals 1. Do you guys agree? It's pretty challenging to put in the calculator. It's not one of those things where, hey, the calculator just fixes everything. So yeah, so it says that toward what point on the coast should he row? Now honestly, I think based on my nicely labeled picture, you probably could figure it out. But you could say, he needs to row 1 mile from the nearest point on the coast. That makes it clear. But I gotta say, like if you had a question like this and you drew a nice picture, or there was a nice picture with everything labeled, and you say, hey, x equals 1, that's actually pretty clear, right? I'm like, all right, what does x stand for? Oh, I see, it stands for that, and look, all right, so that's down the coast, and blah, blah, blah. I think that would make a lot of sense. But if you want to tie it up with a sentence, that makes it, makes it very clear. All right, so what do you think? Questions, comments, thoughts? I hope that stretched out your brains a little bit.
I got
Okay, so have you guys ever, listen up please, have you ever wondered where and how your calculator can figure out x-intercepts? Somebody had to program something in there to make it do that, right? And so when we look at our new topic for the day, Newton's method, this is one of the ways that this could be done. Those of you that are like programmer types, I don't remember exactly what I had on the video as far as specifics, but this is like an iterative process, and so it can be done repeatedly over and over. Doesn't that feel like something a computer would be better suited for? And so using a computer or a calculator, some kind of a programming device, you could really make this fast, right? And so this Newton's method, I feel like the further you go in math, the more you take the curtains away from the window and you can see more stuff. Like when you're in Algebra 1 and you first learn about quadratics, all of them factor really nicely, right? And then you open the curtain a little bit more and they're like, whoa, some of them don't factor. Maybe we should use the quadratic formula, or maybe the completing the square or something like that, right? And then you open the window even more and you start to find equations that are even tougher, right? And you're like, whoa, new technique needed. The truth is, if you open the window even more, you find out that most of the equations out there, you can't solve them analytically. They're just impossible. There's no technique. In fact, it's been proven, and I don't get this proof, it's been proven that above, think about this, when you get a polynomial above a 5th degree, so 6th power, 7th power, there is no analytical method for solving those. So it's actually been proven. And when you think about it, to prove that something does work, that's one thing. But to prove that nothing will ever work, that means that you've considered all possibilities. So supposedly there's a proof, and I don't know it. It's like a PhD level kind of thing, and who knows, right? But it's been proven that there's no method even for that. So when you start looking at things like what we're going to do today, example number 2, and you look at that equation, it's a mix of a polynomial and a trig function. You gotta admit, it's like, man, it doesn't seem very likely that there's going to be this cute little process. Well, hey, just substitute this into that and divide by that and blah, blah. I mean, it seems pretty clear that you're not going to be able just to solve this. And so what do you do beyond just sort of guessing and checking? Graphing, right? You could start plotting some points and you could get kind of close, but maybe there's a better way. Newton's method would potentially be one of those ways. Newton, of course, is the one credited with this. There are others that certainly lent their expertise. So it's been a while since I made that video, so I don't remember exactly what's all in there. Somebody was asking me about the IVT. So was the IVT in that video a little bit? So I think that that's a pretty nice place to start. It could be a total needle in the haystack, though. Please know that I'm not going to do something like that to you on purpose. Needle in a haystack, in other words, you're looking for sign changes in y. And so if you start picking the wrong numbers, then this could turn into a total needle in the haystack. Just know that I'm going to keep the numbers like around 0. Like, it's not going to be like, sorry, you didn't pick 21/16. That was it. If you would have just picked that, it would have been a lot easier. Not going to do that to you, okay? So I'm going to suggest here that we, start off with an easy number like 0, like x equals 0, and just kind of see what happens. So I'll write f of 0 equals, you know what, I'm going to change something here a little bit. Whoops. Hang on. So what would f of 0 equal? -1. Agreed. Sorry, I'm going to use my calculator here. Okay, there we go. Will that work? That'll maybe work. Okay, let me just quit that for a second. Okay. Okay, so here we go. So f of 0 equals -1, which is less than 0. Looking for roots here. That's what Newton's method will help us with. What would be another, in your opinion, smart test number? 1, -1, 2, 3, 4, 5. You know what I was thinking? How about pi? Pi. Like, we could do a lot of this without a calculator. We could do this in our head real quick. If you tried pi, because like cosine of 1, I don't know what that is, and probably neither do you unless you look at a calculator. But I do know what cosine of pi is. So how about f of pi? All I'm looking for is a sign change. It doesn't have to be, I want them to be relatively close to each other, and 0 pi are pretty close to each other. What's f of pi? Pi cubed plus 1, yeah. And so the important thing about pi cubed plus 1 is that it's bigger than 0. I know that x cubed is continuous. I know that cosine of x is continuous. And so by the IVT, doesn't there have to be a value where y equals 0 somewhere in between? Between 0 and pi? And so we take a guess. Somewhere between 0 and pi.
2.
Keep it easy. A 2?
1.
A 1? What do you guys think? 1 or 2? We're going to start using our calculator, so I'm not too worried about like pi over 2s and all that. Let's go with 1, I think. It's either going to be a 1 or a 2. To me, makes the most sense. Maybe a 3. 1 is nice and easy. So what I'm going to do here is start off this process, and I'm going to say that my initial guess is x is equal to 1. And as you guys know, Newton's method is iterative. Here's the formula. Our x intercept, our estimate of it at least, our first one is going to be x0 minus f of x0 over f prime of x0. So that's our little formula for Newton's method. It does come from the slope formula or the point slope equation, however you want to look at it. That's our formula. And my initial guess is going to be 1. And I'm going to use my calculator extensively here. So I'm going to say x1 is equal to 1 minus f of 1 over f prime of 1. So here's what I'm going to do. I'm going to go, oh, it's not going to let me do this. I hate that. So is it okay if I erase the writing real quick? We'll put it back up there in a second. So I'm going to go back over here and I'm going to say that y1 equals, we're going to make it x minus parentheses x, bless you, cubed minus cosine of x divided by the derivative of that. So divided by parentheses 3x squared plus sine of x. So I basically put Newton's method in there for my y1. Does that make sense? I'm going to do some button pushes you may or may not have seen before. I hope you've seen some of them, if not all of them. I'm going to quit out of this. I know that Newton's method is in there. So what I'm going to do now is I'm going to use Newton's method, and I'm going to do it like this. Have you ever seen this button push? Alpha trace. Alpha trace will give you your y1, y2, y3. It's just a few less button pushes than the other way. So if you go alpha trace, I want to use y1. And what do I want to plug into my Newton's method formula? My initial guess, 1. So I'm going to do y1 of 1. I hit enter, and I get 0.8803. So I might write this. This will go away here in a second as well. I apologize for that. I might write something like x1 equals 0.8803. And I'm actually going to do this just for my own sanity. I'm going to write equals a. So this is my first estimate using Newton's method. My guess was 1. Here's my first iteration. I got 0.8803. So for my second one, I'm going to write x2 equals a minus f of a over f prime of a. From a notational standpoint, does that make sense? You're totally okay doing that. So I'm going to do a corresponding action on my calculator. And again, you may or may not have seen this. I'm going to say that number that I just got, watch the button pushes, I'm going to go store alpha, what am I going to call it? A, store alpha A. And so that means from there on out, anytime I type A, it's going to refer back to that specific number. So what am I going to do now? Kind of another cycle, right? So I'm going to go alpha trace y1, but I'm not going to do y1 of 1, I'm going to do y1 of A. There you go. y1 of alpha A, and I should get a slightly different number here, 0.8656 ... So that's after 2 iterations. Are you starting to see this? So I want to store that number. I think maybe I'll store it as a different number. Maybe I'll call it B. Yeah. So I'm going to go store alpha B. And then how many more times do I have to do the Newton's method process? One more time. So I'm going to go alpha trace y1 of not 1, not A, B. So alpha B. And since it asks for 3 iterations, this will be my final one, 0.865474076. So what do you write here? Like all those things that were like, I had them up there, then they got erased because it's kind of a pain, but I like the video here. In the end, you're going to write, x3 equals B minus f of B over f prime of B, and that equals 0.86547. I don't know how close that is, but I'm guessing it's, do you see how it didn't move very much? Like when you start to get really close, the decimal is not going to go, it's not going to really jump too far. And you can see we've gone from like 0.88 to 0.86547. So we've got to be pretty close right now. You could use the zero finder on your calculator to compare. Newton's method, given enough iterations, is actually more accurate than the zero finder. Like if you just kept on doing more and more and more iterations, it'll get better and better and better. And eventually, it'll go all the way across the screen and would continue to get better even on the digits you couldn't see. So, and if you were a glutton for punishment, you could do it all by hand and figure out what those digits are. I don't even know how you do that. It would be really painful. Yes, it would. All right. So, guys, that's it for Newton's method. I'm going to post this video if you want to see that process. Then again, you're certainly welcome to it. Brendan. Pull up the graph screen? Yeah. Sure. So I basically put in x minus f of x over f prime. So basically I could run that, cycle all my numbers through that. Yeah. And you could start over from scratch on all of them, but I like that because you just got to go y1 of 1, y1 of A, y1 of B. And you can have a C, D, E, F if you want to. It's not that big hard. Cool. All right, hey, see you guys. Hope you have a good rest of your day.